much more thoroughly than what we would cover here. Okay. This is supposed to be a brief, emphasis on brief overview of the topic of work. This is not an in-depth. Okay, so it's not exhaustive. Okay, this would be a whole chapter in a physics book. Okay, and especially a physics book that, you know, is a calculus-based physics or a engineering-based physics class. Okay, work would, this again, this is I cannot teach the entirety of the concept of work in an hour and a half. It's not going to happen. This is a brief overview. So if you go to a homework question, you're like, hey, he didn't cover this in class. Well, that's because there's a whole swimming pool of information about work, and I can't cover every single type of work problem out there. I'd be here for, it would take me 6 months. So we're going to do a few problems, and the type of problems that you would have on the exam with regard to work are of the few problems that I'm going to cover in class. Okay, the homework may have a few extras thrown in there, so don't freak out. You know, they're just there to challenge you and for you to do some research on your own and to read the book a little and to say, okay, how would I apply this concept here? Okay, but know that on the exam, I'm only going to give you the problems that I've gone over in class. Okay, does that make sense? Okay, it's again, this is just supposed to be a brief overview, not exhaustive of the topic. And this is not a physics class. Okay. I even write that in my notes. It says, beyond the scope of this course to even begin to cover all the situation scenarios for calculating work done over a dynamic system. Okay, let's start with the definition of work. Work is force over distance. Okay, it's force over distance, which is mass, and force is mass times acceleration okay, times distance. Okay, it's mass times acceleration times distance. Because remember Newton's famous second law, it's F equals ma, right? Like, of course, everybody knows that. Okay, force. If I hide myself, can you guys still see me? If I go like this, can you still see me?
Yes, sir.
Okay, perfect.
Yes, we can.
What if I do this? Can you still see me now?
Yes, sir.
Yes.
Okay, perfect. Thank you.
Yes.
Awesome. Okay. So work is equal to force times distance, mass times acceleration times distance. Okay. Force due to gravity okay, is weight. And weight is equal to mass times the acceleration of gravity, mg. Okay, where g is the acceleration of gravity. G is the acceleration due to gravity. Okay. Okay, in SI units, okay. Okay, I forget what SI stands for. Standard something, standard imperial, I don't know, something.
Index, maybe?
What is it?
Is it standard index?
Index? Maybe, just Google it. SI units. In SI units, okay, it's standard, it's just a metric system, basically. Okay, it's what everybody uses except for us and like one other country. Okay, because Americans are weird and we want to be special. So we don't use the metric system. Okay, but the SI unit is basically the metric system, and the mass, okay, is in kilograms. Okay, G is roughly 9.8. In this class, we're going to do 9.8. I know it's like 9.81 or some odd, number of digits that you can go out, but whatever. In this case, it's going to be 9.8 meters per second squared. Okay, that's the acceleration due to gravity. That's how fast you fall. Okay, weight is mg. Which is going to be a kilogram meter squared. Okay, kilogram meter. Let me think about this for a second. It's kilogram meters. No, not squared. Sorry. Kilogram meter per second squared. Okay, and a kilogram meter per second squared has a special name. Anybody know what that name is? For all you engineering people?
Is it newtons?
It is Newton. Very good. It's Newton, okay? Like my cookies. Okay, Newton. It's a Newton, N. Okay, work is just force over distance. And force, okay, is MA, which is a Newton. This is a measure of force. And so work is force times distance. Okay, force dotted with distance, which is equal to the kilogram meter squared over second squared, which is a Newton meter, which is a, I know what a Newton meter is? It's a joule.
Joules?
Yeah, very good. Thank you. It's a joule. Okay, J for joule. Okay, in imperial units, this is American units. Okay. Okay, in imperial units, okay, mass is in pounds mass. Okay, mass is in pounds mass. Okay, which is very confusing. Okay, it's pounds mass. That's interesting. Okay. Which is really not used. We don't use pounds mass unless we were to talk about your mass on a different planet. Okay, then we would have to use pounds mass. Okay, but us Americans, we're very egocentric. We think that we're the best and the world revolves around us. And we're not going to any planets anytime soon. So we don't ever really use mass in pounds mass. What we do is we jump right to force. We skip pounds mass and we go right to force. And we say that G is in 32 feet per second squared. That's the acceleration of gravity. Okay, in feet per second squared. Okay, but we jump directly to weight, which is basically your mass on planet Earth. Okay, is your weight, and that's in pounds. This is mg, which is in pounds. So if you were to go to a different planet or go to the moon, your weight would be different than pounds. You could not measure your weight in pounds on the moon. Okay, you'd have some pound mass times the acceleration of whatever the gravity constant is on the moon. Okay, so yeah. So SI units is a little bit nicer to work in, and that's pretty much what we're going to work at. Okay. And this is weight, not mass. Pounds is weight. Okay, so when somebody asks you, how much do you weigh? And you say, I weigh 132 pounds. Well, you're correct because you're on Earth. But if you were to go to Mars, you would not weigh 132 pounds. You would weigh something else entirely. And it would have to be in different units. Okay. Okay, so aka pound, it would be pounds force is what this is. It's pounds force. Okay, so you could say pounds mass or pounds force. And pounds, the pounds that we talk about in common language is really pounds force. There's pounds mass and there's pounds force. One just doesn't have a feet per second squared and one does. So yeah, very confusing. The British are confusing, okay? Sometimes I watch Doctor Who. I don't know what the heck they're talking about. Okay, they're confusing. And I apologize if there's anybody who's British in here. Okay, but y'all are confusing. So we talk about, okay, work in the imperial system, and the British don't even use the imperial system anymore. That's how messed up it is. Okay, they got rid of the imperial system long time ago when France went to it. When France went to the metric system, they're like, oh yeah, that makes more sense. So they got rid of the imperial, and Americans, we just stuck with it because that's what we do. We just are in it to win it, and we stick with things way too long. I guess, I don't know. Okay, so work is equal to pounds times feet. Okay, or what we would call a foot pound. Okay, so instead of a joule in the SI unit system, the joule work is in foot pounds in SI. Okay, and what's interesting is that they're about the same. So 1 foot pound in the imperial system is approximately 1.36 joules. So that's kind of cool. Okay, I'll put a little approximately. Okay, so yeah, there's a conversion between, and it's roughly the same. So I mean, within, a little bit extra, but I don't know, all roads kind of lead to the same amount of force that's being applied to a system. So another interesting thing is that sometimes mass is unavailable. We don't know how much mass we have available. Maybe it's because we're using imperial units, or maybe we just don't know what the mass is. Okay, mass is, this should say unavailable, I'm sorry. Unavailable. Okay, and so, but, and here's the big but, density is available. Why is density available? Because we basically know what the density is of everything that's on Earth. Okay, there are monks that sit and calculate the densities of basically every compound that we've come up with. And so we know what the density is. So if you're able to measure the volume of something by just dipping it in water using Archimedes' principle, you just dip something in water and you find the volume of that, you could find, and you know the density, like what the density of lead is, or what's the density of copper, what's the density of gold, or, if I want to make lead into gold, how do I have to change the density? Because I really want to do that. It's not possible. That's called alchemy. But if you want to turn lead into gold, then you would have to know the density of lead. You have to know the density of gold, and those densities are going to be different. Okay, so we basically know what the density is, and that's mass over volume. So if we could use the density, and if we have the density and the volume, we could solve for mass by just multiplying d times v equals m. And so then we just get mass. Okay, so we can solve for mass. Does that make sense? Yeah, it's good. It's all good in the hood. Okay. Okay. Okay, number one. We need calculus when the force varies with the distance. Traveled. Okay, we need calculus when the force varies with the distance traveled. If the force doesn't vary, if the force is constant, then we don't need calculus. It's an algebra problem. But if the force varies, then we need calculus. Okay. So let's do a couple of work problems that deal with calculus. Okay, problem number one. Okay, when a particle is located, okay, distance x feet. Oh, we're using imperial units, so scary, scary times. Okay, when a particle is located distance x feet from the origin of a force, of x squared plus 2x pounds, okay, is exerted on it, the origin, oh, this should not say of, sorry. It should be a force of x squared plus 2x pound is exerted on it. Okay, so here the force varies. Okay, the force is not just a constant. The force is varying depending upon how far out x I am. Right? So how much work is done by moving said particle from x equals 1 to x equals 3. So we're moving the particle 2 units. Okay, so work.
Professor, looks like somebody has their hand up.
Oh, yes, America?
Sorry, is that x squared plus 2x or 1x?
2x.
2x? Oh, okay. Thank you.
Okay, so work, moving an object from A to B, A to B, sorry, with varying force has equation work equals the integral from A to B of f of x dx. Okay, so we're just going to say the work is going to go from 1 to 3 of x squared plus 2x dx. Okay. So this is the force over the distance. This is the force. F of x is the force, which varies depending upon x over the distance from 1 to 3. Okay, but we have to integrate because the force is variable. So this is gonna become x cubed over 3 plus x squared over 2, 2x squared over 2, which cancels. Evaluate it from 1 to 3. And so we get x cubed, I'll just plug it in. 3 cubed over 3 plus 3 squared minus 1 cubed over 3 minus 1 squared. So 3 cubed is over 3 is 3 squared, which is 9, plus 9. Okay. Minus 1/3. Oh, this should be plus, I'm sorry. Plus 1. Okay. So, I don't know how we want to do this. Distribute the negative. This is 18 minus 1/3 plus 1, or minus 1. That's 17 minus 1/3, which is 16 and 2/3. Okay, and what's the work? What's the unit here for work? It's foot-pound. Okay, because we were in imperial units. Because the distance was in feet. Okay. Let's talk about springs. Hooke's law. Okay, the force required to maintain a spring.
Professor, what's the name of the law?
Hooke's law.
I,
Hooke,
oh,
like
okay, okay, okay. Thank you.
sorry. Sorry, Hooke's law. The force required to maintain a spring stretched x units beyond its natural length okay, is proportional to x. Okay, that is, okay, f of x is equal to kx. Okay, so there's some proportionality constant k. So this is linear. It's a linear, right? So the force goes up linearly. Okay, and the slope of that force is just k. Okay, so m is equal to k. So the slope of that line goes up. But if I'm out further, the further I go out, the more force is applied, right? So you think of this a spring, right? The further you go out on the spring, the more tension that spring is applying. Okay, to a point where it'll actually, you know, forget the technical word, but it basically it dies. The spring collapses. Okay, but it's linear. The force is linear. Okay, but it is variable. And so if we wanted to find the work done, right, it would be the integral of the force, which would be the integral, the work A to B of kx dx, right? So that's how we find the work done on a spring. Okay. Okay, so let's do a problem. Number 2. Okay, a force of 40 Newton Okay, we're back to SI units, which is good. Anybody figure out what the I standard for? Was it index? No? Whatever. Okay, a force of 40 newtons is required.
Oh, Professor, it means System International.
System International, okay, thank you. Awesome. Okay, so yeah, we and one other country, I forget which one, do not use that system, but the rest of the world does. Okay, so force of 40 newtons is required. Okay, to hold a spring that has been stretched from its natural length of 10 centimeters to 15 centimeters. Okay, so its resting length is 10 centimeters. And then we're pulling it to 15 centimeters. Okay, how much work? Maybe think of like a ballpoint pen. Okay, where we have a spring that's naturally stretched out 10 centimeters, but then we're gonna push it an extra 5 centimeters. Okay. And so the natural length of 10 to 15, how much work is done in this stretch? Okay, how much work is done in the stretch? Okay, so, well, we have f of x is equal to kx, right? So what? Well, we got to figure out what k is, okay? So, and we also need to reconcile our units here. We have a force of 40 newtons, right? But what is a newton? Isn't a newton a kilogram meter per second squared? That's in meters. And we're using centimeters. So we've got to convert. So x here is going to go from 10 centimeters, right? Well, not x, it's just 10 centimeters is 0.1 meters. Okay, to 0.15 meters, right? Because we just have to make sure we're in the right units. And we got to figure out what our spring constant is. Okay, if it's resting state, I can't draw a spring, sorry. Let's try to draw the spring. Okay, if its resting state is 10 centimeters or 0.1 meters, okay, then it takes 0 force to make it go 10 centimeters. What we're doing is we're saying, okay, we're taking this spring that's at rest and we're going to hang some sort of weight from it, or we're going to pull it with our finger. Okay, and we're going to move this another 0.05 meters. Okay, that's the total distance that I'm covering. Okay, so we start at 0 meters and we end up moving it to 0.05, another 0.05 meters. Okay, because the 10 centimeters, that's just at rest. Okay, that we get that for free. Okay, so we're gonna zero that out, and so this is really, we're going from 0 to 5 centimeters. Is the distance that we're actually doing work over. So the force that's required to move this 0.05 meters is 40 newtons. So if F is equal to Kx and 40 is equal to K times 0.05, then if I divide by 0.05, okay, I get K to be equal to 800. Okay, and so that's K. Does that make sense? Because we're only moving over 0.5 meters. Okay, thank you. Oh, awesome. Thank you, Shala. Yeah, Myanmar, okay, which used to be called something else, but and Liberia. Oh, Liberia, do you know what? Like that makes sense that Liberia uses it. You know why? Because the United States created Liberia. Okay. You can read about the history of Liberia. Basically we said, hey, we're gonna conquer the coast of Africa here, and we're gonna let all the people that we enslaved go back to Africa, and we're just gonna call that place Liberia. So we brought them to the United States, and then we said, oh, by the way, you can go back to Africa if you want, now that you're all free, and we're just gonna set up this little colony called Liberia. And then Burma, yeah, Burma and Myanmar, they use that as well. So yeah, so basically the United States, the country that we created in Africa from the United States, and Myanmar, which used to be called Burma, those are the ones that use the imperial units. Okay, and I think Myanmar was because they were occupied by the British. And so, yeah, so that's how they got their imperial units, was the British occupied them, said, you're going to use our units. And then what happened? And then the British didn't even use those units. So they just got stuck with them. So yeah, so little interesting. Oh, that's cool. That's cool. Yeah. Yeah, very cool. Yeah, makes sense. Okay. Weakness. Are you sending the chat to me or everybody? Everyone. Okay, perfect. Thanks. Okay. Yeah, low history. Low history goes a long way. Yeah, you know, like, yeah. Crimes against humanity. Okay. Awesomeness. 800 this is not a history class though. Let's get back to the math. And it's a physics class today, so we can digress a little bit. So this F is going to be equal to 800x. So there we go. So how are we going to find the work done? The work being done is going to be from 0, not 10, okay, 0 to 0.05, okay, 800 over the force 800x dx. Right? Okay, so there's more chats. Okay. Okay, so let's come back. Okay, thank you, Ashley. Okay. This one's really easy. This is going to be 800 x squared over 2. Okay, which is going to go to 400 x squared, 0 to 0.05. 400 times 0.05 squared. Okay, evaluated from, I mean, if I'm just gonna, if I plug in the 0, I get 0. I'll just plug in the 0. Boom, 0. Happy? Great. Okay, I mean, I'll do my due diligence. There we go, 0 squared, nice, okay. But this guy's gonna go to 0, so I don't really care about him. Okay, and so what's 400 times 0.05 squared? Yeah, thank you, Eric. Yeah, it's 1. It's 1. 1 what?
It
Yeah, like a-
pounds.
Per
Nope.
meter squared.
Nope,
Fourth
Is it a Newton?
fourth pound, right?
say it again.
Joule. Like
Nope.
joule.
It's joule.
Yeah.
It's 1 joule. So our answer was 1 joule. That's kind of cool. Okay. Let's get a little spicier. Okay, number 3. A 200-pound cable okay, is 100 feet. Long. And hangs vertically. You could say this is vertically off the side of a building or whatever, however you want to. Okay. So this hangs vertically. Okay. How much work is done by pulling the chain all the way to the top? Okay, so. And, you know, it could be a building. I'll draw a building. Here we go. Here's a building. Okay, and then we've got this chain. Okay, we've got this chain that's got these links and all the way down, okay, until the ground. Okay, boom. Okay, and what we want is we want to know how much work is it going to take to pull that chain all the way up to the top of the building. Okay, the chain and the building are 100 feet. It's a 100-foot tall building, 10-story building. Okay, and I've got this chain. Okay, then I want to pull all the way to the top of the building. Well, what happens as I start pulling the chain up?
Gravity.
Gravity happens? Gravity's always happening.
You
The
lose
rest of the
weight.
chain is left is lighter.
Yeah. So as I pull this up, it's gonna get lighter and lighter and lighter and lighter and lighter and lighter, right? Does that make sense? So I'm gonna say that the mass of this thing changes over the distance. Okay, because I have less of the mass to pull up. As I pull it up, okay, I have less of the mass to pull up. Okay. Okay, so the work is the force over distance. Okay, and I'm gonna let X, the work is the force over distance. And I'm gonna let X be the distance, okay, from the, is it from the top or is it from the bottom? Let me just think about this for a second. I just wanna make sure I get the word right. My diagram's correct, but I just wanna make sure I get the wording correct. So. Yeah, it's the distance from the top. Yes, distance from the top.
Professor, I have a question.
Yeah,
Wouldn't we also need to know the height of the building?
yeah, it's 100 feet.
Oh, okay.
We don't really need a building. Okay, we could say that a helicopter is pulling the chain up. It really doesn't matter. Okay, I'm just saying that I'm on top of a building. It's 100 feet. The chain is 100 feet, and I'm gonna pull it up all the way up. Okay. Okay, so the x is the distance from the top. So understand the frame of reference here. The frame of reference is that this guy here, this link down here, he's gonna have to travel 100 feet. But this link up here is not gonna have to travel 100 feet. Does that make sense? It's only the link at the very bottom of the chain that has to travel 100 feet. So the distance is gonna be measured from the top, not from the bottom. Okay, so the further down that I go, the more distance I have to travel. The further the links are down on the chain, the more distance I have to travel. Does that make sense? Somebody give me an amen. I'm just kidding. Okay, yes, no. Okay, I'm just I'll
Yes.
thank you. Thank you for class participation or precipitation. What is no participation? Yeah, thank you for the class precipitation. Okay, so x goes from 0 to 100. Okay, x goes from 0 to 100. Okay, so how are we going to know what the force is at any given instant? Okay, so for any given instance, okay, we'll call the distance that any specific link has to travel as x. Okay, and so if we're already x up, then that's going to be 100 minus x. Okay, for what would be remaining? Okay, so x has already happened, and we've got 100 minus x left. Okay, and then we're going to say, well, what's each link? What's each link in terms of, you know, it basically we're thinking in terms of what's called a delta x, or a very small x. So basically, what is 1 foot? Every foot, what's the rate of the force? What's the rate of the force? Okay, or the force of gravity on this thing. Okay, well, we have weight in imperial units, which is pounds. It's 200 pounds. Okay, but that's spread over, okay, over 100 feet. So the weight is really 2 pounds per foot. And I could multiply that by whatever fractional amount, okay, of the chain. I could multiply it by a fractional amount to get the weight of any length of chain that I would want. Does it make sense? So it's 2 pounds per foot, basically. And if I wanted half a foot, then it would be 1 pound. If I wanted 3/4 of a foot, it would be, I don't know, whatever 3/4 3, it would be 1.5 pounds. Does that make sense? So this is kind of my rate of weight. that I'm gonna use. 2 pounds per foot times whatever fractional amount or times whatever multiplier that I would use to get the weight. So we're gonna let that be our delta x. Our delta x is 2 pounds per foot. That's just basically we can use that as every link in our chain. Okay, we'll have a weight of 2 pounds per foot times whatever distance is left over. And what's the distance left over here? Okay, or what we're gonna call the remaining force. This is my delta x. So the remaining force is gonna be my 2 pounds per feet times whatever my remaining force is, what my remaining distance is. And we're gonna call that remaining distance 100 minus x. Okay, because that's our frame of reference. It's this guy here is the remaining distance. Okay, and that's gonna be for every little particle on this chain. Every molecule on this chain is gonna have a remaining force of 2 pounds per foot times however many feet I have to travel every molecule up this chain. Okay, so as it goes, and I'm pulling, okay, however many, fractional feet of chain that's left, I'm gonna multiply that by how 2 pounds per feet, and subtract that from 100, okay? And that's gonna give me, okay, my remaining force. Okay? So, how do we find the total work done? Okay, if the remaining force, okay, this W is not work, by the way, it's weight. Okay, so, okay, the remaining force is going to be 2 pounds. This is my f of x. So the work done is going to be the distance that I travel, which is 0 to 100 feet. Okay, the very first link doesn't have to travel anything. The last one has to travel 100 feet. So the total distance that we're traveling over is 100 feet. And then it's 2, that's for the weight, times the distance that is being traveled for all of the remaining links, which is 100 minus x, and then we're going to integrate that. Okay. So that's the setup. So this actually, the integration is really easy after we set it up properly. This is 200 minus 2x. Integrate from 0 to 100. This is 200x minus x squared. You're like, where'd the 2 go? Well, here. It's 2x squared over 2. Boom, boom. From 0 to 100. Okay, if I plug in 100, I get 200 times 100 minus 100 times 100. Right, which is just 100 times 100. Because if I factor out 100, I get 200 minus 100, which is 100 times 100, which is 10,000. And so this is 10,000. And what are the units of work in imperial units? This is my work, the work that I did. That's the force over distance. That's the weight, which is mg, over the remaining amount of weight that I have left all over that
feet-pounds?
distance.
Foot pounds?
Yeah, it's foot pounds. Thank you very much. Foot pounds. Usually they have a little hyphen in between because it's foot pounds. Feet pounds. Okay. It's not pounds per foot. Don't get that wrong. It's not pounds per foot. It's foot pounds. It's feet multiplied by pounds. Okay. Okay. Where are we at with time? Okay, we got a half hour, right? Okay, good. That should be hopefully just enough time to finish our last problem. Okay. Okay, number 4. Again, this is not supposed to be an exhaustive, topic on work. It's just, here's 4 problems that we can do with calculus and with work, the topic of work. Okay, so number 4, a tank has the shape of an inverted circular cone right, with a height of 10 meters and a base radius of 4 meters. It is filled with water to a height of 8 meters. Find the work done or sorry, find the work required, I should say, to empty the tank by pumping all the water to the top of the tank. Okay. Okay, so good stuff. Good stuff. Okay. So force over distance, right? Okay, yeah, so we gotta kind of dissect what this means. A tank has the shape of an inverted circular cone. What does that mean? It's basically an ice cream cone. Okay, we take a cone and we invert it, flip it upside down. So let's take a cone and let's invert it and flip it upside down. Okay, there's my inverted circular cone. Are there other types of cones? Yeah, there are. Okay, there's oblique cones and there's, yeah, a lot of other ones. But this is inverted, it's circular, we're good. And it says it has a base radius of 4. Okay, that means that the base, which is now flipped upside down, has a radius of 4 meters, and it has a height of 10 meters. And I'm actually gonna bring that line back, but not the 10, because I'm gonna actually put the 10 on the outside here. This is 10. So that's 10. Okay, but what I am gonna put on the inside is I'm gonna put the 8. Okay, this is filled up to 8, right? And so we get this guy here. Okay, and so this is, this is my wavy water. Okay, maybe I won't put the water in. Okay, but just know that that's water. Okay, I don't want my diagram to get too messy. Okay, so this is filled up to a height of 8, whereas the original was filled up to what is 10. Okay, the tank is 10. Okay, this, I'll put it in a different color. This guy, which is in green, okay, only goes up to 8. Okay. All good? Okay. Okay, but I'm gonna table the 8 for right now. Okay, and maybe I'll go over here and put 8. 8 meters, there we go. That makes me happier. Okay, because, let's think about this. What's the distance that the water has to travel at the very beginning? Because I'm pumping this to the top, right? I gotta pump this all the way up, right? The water's gotta come all the way up, and then it's gotta be pumped over this side here. Maybe we have a little spigot, okay? It's gotta come, it's gonna drip over the side. Okay, so I don't know. I can't draw. My daughter's the artist of the family. Stop dropping the roll. Give my stuff back. Stop stealing my stuff. Stop. The frick. Give me my cone back. So initially the water has to travel 2 meters, right? Initially the water has to travel 2 meters. And at the very end, the water has to travel how many meters?
10.
10 meters. Thank you, Ashley. Very good. Okay, so in the beginning, it's got to travel 2 meters. Okay, so the distance this thing has to travel is either 2 to 10 meters. Okay, it's good. Okay, and so, well, what's the mass of the water? What's the mass of the water? Right, so then we need to find the force, which is mass times mg, right? Mass times the acceleration of gravity, mass of the water. Huh. Well, we don't have the mass of the water, but here's what we do have. We do have the volume of the water, right? We have the volume of the water and its density. What's the density of water? What's the density of water? Anybody know? Are you dense? 80?
Uh, 1 gram
Is it
per
mass
cubic
over
meter
volume?
squared.
Okay, no. I think Jackson, was that you or was that somebody
Yeah.
else?
Yeah,
Okay,
1
Jackson.
gram. 1 gram per cubic centimeter.
Yeah. Okay, so did you look that up or did you know that?
I looked it up.
Oh gosh. Okay, cheater. Okay, it is 1 gram per cubic centimeter. Okay, it's and CC, right? So when they talk about CCs, like, you know, oh, this was 1 CC, that's a cubic centimeter. Okay. So 1 gram per cubic centimeter. But what? What's the big but? Our units are off. So this is actually 1,000 kilograms per cubic meter. So we're going to use the kg, right? Because we wanted this in newtons. Okay, remember those tasty little cookies? We want this thing in our newtons. Okay, so this is the density of water in those SI units that we're needing to have. So that's the density of water. Okay, that's cool. Coolness. Okay. So now we just need to find the volume. Oops. Stop. Okay, now we just need to find the volume. But the volume is kind of tricky. Okay? The volume's kind of tricky. Think of each of these disks as a single sheet of water. That's one atom in width, you could say. We have a sheet of water that's 1 atom in width, and we're going to pump all of those sheets, but those sheets live at different depths, don't they? Each sheet of water that I have to pump out of the tank lives at a different depth, right? So if I talk about this sheet of water here, okay, which has a delta X, okay, of depth to it, that will give me a volume. It's a circular sheet that has an area of a circle, but it has a depth of delta X, which creates a volume. It's a disk. It's that little discs, and we're gonna take smaller and smaller and smaller discs of water up and out of the tank. Right? So this is a volume. It's a volume. It's a sheet, right? Okay. So what's the volume? The volume is going to be equal to pi r squared times my third dimension, right? That's the area which is pi r squared times that delta x. That's going to give me my depth, my third dimension here. But I'm going to let delta x go to 0. Basically, one atom one atom sheet at a time is going to go up and out of this tank. Okay. So the volume is pi r squared delta x. Okay. But we need r in terms of x. Okay. 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 We need r in terms of x. Well, how can I find r? How can I find the radius of this one sheet? Okay, maybe I'll put that in black. Let's go to black. Okay, so here's my radius of that one sheet. I'll call that r. So r, that one sheet has radius r. It lives at a certain depth. What is that depth that it lives at? Well, if it has to travel x units all the way up and out, then it lives at a depth, okay, of x, then what's remaining here is 10 minus x. Right? And so what we can do is we can get something called a similar triangle. Okay, we have a similar triangle where x is the distance. Remember, x is the distance that sheet of water has to get pumped out of the tank. But how much, where is it living? It's living 10 minus x units as at a height. We call that maybe the height of that right triangle, right? And so what we have is we end up with similar triangles. We end up with, okay, a big triangle and a small triangle. The big triangle has units of 10 by 4. Okay, right? So the big triangle is a 4 by 10. The small triangle is an R by 10 minus x. Okay. Maybe I'll do 10 minus x here. Okay, and so what we can do is we can set up a proportion based on similar triangles. We could say 4 to 10 is equal to R to 10 minus x. Look at that. Now we can solve for R. Okay, and we get R is equal to, multiply both sides by 10 minus x. And we get R is equal to 4/10, which is 2/5, times 10 minus x. So now we have R in terms of x. That's what we wanted. So what's the volume? What's the volume? The volume, okay, is going to be equal to pi times R squared. Well, what's R? R is 2/5 times 10 minus x quantity squared. Okay, times delta x. That's my one atom depth of volume. Okay, so it's a one atom deep sheet. Okay, and that's my delta x. That creates my volume. Okay, that's my disk. Okay, I've got a disk, and it has volume of delta x, and it has a width of delta x. Okay, area of pi r squared, width of delta x. Okay, that's my volume. But what do I need for work? What do I need for work? For work, I need force and distance. I don't need volume. I need force and distance. And especially for pulling something up, what are we working against when we're pulling something up? Aren't we working against
Gravity.
gravity? Thank you. So isn't this mgd? Isn't that work? Mass times acceleration of gravity. We don't know mass though. But what do we know? We know volume. And what is mass? Isn't mass just volume times density? Right? So that D is not distance. That is D for density, not distance. Maybe I should have a capital D for density. VD, which is volume times density. So how can we get our mass? Well, can't we just multiply the volume by 1,000 kilograms per meter cubed? Wouldn't that give me my mass? So let's pull this all together. The work done here is the mass, which is the V times the density, which is just the volume times the density times the acceleration due to gravity over the distance traveled. Okay. Okay, good. Okay. And so, we have the volume, which is this pi. Let's talk about let's pull in the density, and these two, the D and the G, those are just constants. This is 1000 times 9.8. Those are just constants. V is pi times 2/5 times 10 minus x quantity squared. Okay, delta x, we'll talk about the delta x in a minute. Okay. Okay. And then over the distance, right? Over the distance. Okay, this delta x, okay, really becomes an x. It becomes, it's the distance of each particle, okay? It's the distance that of each particle. And so when we set this up, we're going to take a particle, and we're going to take all particles between 2 feet and 10 feet deep. Okay, from with 9.8 times 1000 times pi, those are all constants. I could square the 2/5, that would give me 4/25 times 10 minus x squared, and this delta x there, that actually translates into an x. So we have to put an extra x there. Okay. Because that's the depth of each of my particles. And we have volume. If we don't have that x there, then we're just going to end up with area. We don't want area, we want volume. And that's over the total distance here, travel. So make sure you plug in that x. And now we can just do the calculus. Okay, the setup here was the hardest part. Okay, if I multiply 9.8 times 1000 times 4 and then divide by 25, I get 1568. Stop. 1568 pi. And then I'm going to take this 2 to the 10, and this is going to become 10 minus x squared times x dx. Okay. So we get 1568 pi. Okay, this is going to become, I'm just going to multiply this out. This is going to become 100 minus 2x plus x squared, all times x dx. This is 1568 pi. Okay, and this is 100x minus 2x squared plus x cubed, right? From 2 to 10 dx. Now I can integrate. Okay, this becomes 100x squared over 2 minus 2/3 x cubed plus x to the 4th over 4 from 2 to 10 is 1568 pi. Okay, and this equals, okay, plug in the 10 and then plug in the 2. I'm going to move this over, this equal sign over, so I have room, extra room. So this is going to be, well, that's just 50. So this is 50 times 10 squared. Okay, minus 2/3 times 10 cubed. Oh, I messed up. This is not 2, this is 20. Sorry. Okay, so this is 20, not 2. My bad. It's 20x. So this is 20. So this is minus 20 thirds times 10. Sorry, minus 20 thirds, and I wrong again. There's a 20 here. 20 thirds times 10 cubed plus 10 to the 4th over 4. Okay. All of that, okay, minus, and then I'm gonna put a 1568 pi on the front here. Okay, all of that minus 50 times 2 squared minus 20 thirds times 2 cubed minus 2 to the 4th over 2. Okay. So now it's just a bunch of arithmetic. 1568 pi. Okay, this is going to be 5,000 minus 20,000 over 3. Minus 10 to the 4th is 10,000 divided by 4, which is 2,500. Okay, I could distribute my negative, and I would get 50 times 4, which is 200, so that's a minus 200, plus 20 times 8, which is 160 over 3. And then minus 2 to the 4th is 16 divided by 4 is 4. Okay, so this equals,
Professor,
yeah,
I think the 10 to the 4 power
oh, yeah, yeah, yeah.
divided
Yeah,
by
that's
4 is
positive. Thank
plus,
you.
yeah.
Thank you. Yes. Perfect. Yes, thank you. Okay. Good catch. Good catch. Okay. So now we've got what? We've got 5,000 plus 2,500, that's 7,500. Minus 200 is 7,300. Right? Minus 4. So 7,300 minus 4, that's 7,296. Minus, and then we've got 20,000 and 160. So if I subtract 160 from 20,000, I get 1940. I'm sorry, 19,840. Come on. Erase, please. Thinking about it. Okay, whatever. 19,840. There we go. We finally get our. Okay, what? Stop. Will you just erase, please? No? Gosh, finally. Okay, so 19,840 over 3. 1568 pi. Okay, and then we have, this is gonna be 21,888. Oops. Oh, I'm not erasing anymore. Program is not liking my erasing, so there we go. Over 3 minus 19,840 over 3. Okay, that becomes 2,048 over 3. It's 1568 pi times 2048 over 3. Getting close. Okay, 1568 times 2048 is 321. 1264, so 3,211,000. Okay. And 264 over 3 times pi, which is roughly 3,362,827.8 joules. Which is the exact answer. Well, the almost exact answer. Because we did round. But it's close enough. Right? Whew. Okay, that was fun. Okay.
I think we have different definitions of fun, Professor.
Yeah, well, I don't know. I mean, it was interesting. I mean, physics can be interesting too. Let me stop my share for a second, and then stop.